Okay, hi everyone. I'm glad to be here today, not to talk exactly about this part, but from the beginning. um, I'll be talking about ChemApp for Python. We have developed a few new features recently, and it's quite interesting to see how flexible ChemApp for Python can be in the cases for process modeling. So the subtitle here of Unbounded Process Modeling really represents what it can do. There are no limits. We have so many applications already, and I cannot cover by any chance all of them. What I'll try to do today is just to give you some introduction to ChemApp for Python, and also let you know on the new cool features we have recently developed. So first of all, before talking about ChemApp for Python specifically, just to introduce also what ChemApp itself is, if you don't already know it, you very likely have already used it. So ChemApp shares the same calculation engine that FactSage uses for the equilibrium calculations. And FactSage actually performs calls to ChemApp constantly in all of those products that you already saw. So ChemApp, in principle, is a programmer's library to perform thermochemical equilibrium calculations, to set up, calculate, and extract results from it. And it's a very, very powerful library provided in many different interfaces, C, C++, Fortran, Visual Basic, you name it. And the thing is, we have grown it with ChemApp for Python. But initially, and this is just a quick example of the functionality how you would normally interact with ChemApp itself. You would have this acronyms for different types of functions, and they are very, very powerful, but at the same time, they are very difficult to grasp because, as you can see, this is not directly translatable, right? So you would need to constantly be looking at the manual, and that's most of the motivation to develop ChemApp for Python came from trying to make this more accessible to new users. And then in ChemApp for Python, those functions are still there. You can also make use of them exactly as they were, as they are for the other interfaces. But this is not the highlight of the Python version. For the Python version, you see this in the basic module, but the Python version is composed of 3 different modules. The basic one, the core module, which contains the components required by the basic and the friendly module. And 2 examples here are the stream state and the stream calculation result, which of course are very much important for the demonstration I'll be doing today. We're talking about streams again. You have been hearing about streams from FactFlow and FactProSim, and they are also available in ChemApp. And then we also have the friendly module where rich components are are available to set up, calculate, and process results. The 2 most powerful and most important ones are the equilibrium calculation and the stream calculation classes. So with the equilibrium calculation, we are then not talking necessarily about streams, but you can set up every possible feature or calculation condition that you also set up in FactSage itself, in Equilib, and even perform phase mappings and have some very advanced options. And in the stream calculation, we then are more aware of streams, initial conditions, and final conditions, and the delta in these cases. So there are a few more functionality or implementations needed to provide this functionality. But they are very much related. And one thing that is quite nice about the equilibrium calculation class is that from the results of any equilibrium calculation, you can also create on the fly a new stream. And that already provides a plethora of options to define initial conditions for streams. Okay, so now more to the point of process modeling, I'll show you or try to explain how flow sheeting works with ChemApp for Python. As I said, this is a programmer's library. You all probably are aware of what Python is. It's a very user-friendly, basically programming language. And But we come from the other end. We are more interested on the processes. And then I just took this as a very simple flow sheeting concept. Flow sheeting meaning how to set up or to think about a model for a process. And this is a very simple way of doing it. So as you saw already with the other tools, right? We have some boxes that represent the starting point, the initial compositions, for example, input composition 1 here and input composition 2. And then we want them to go to a reactor. We want to be able to fetch the results, and probably later you want to split and then do something with output composition 1 and something with output composition 2. And in ChemApp, what is actually going on is the same principles apply, but in the background for all the composition data structures, we make use of the stream state class, as you see here, in all different states, or in all different composition points. And for the results, we make use of the stream calculation result class. But you could, and there are some ways of directly creating a stream input by directly making use of the stream state class, but that is not necessarily so convenient. So what we actually make is, what we actually provide is a stream calculation class to make things even more simple and to create these stream states, and then also to move around these different regions between combining streams to perform a certain reaction, to set up conditions for the reaction, and then to later also manipulate streams in any other way. I will show you this now in much more details. For the secondary steelmaking example, if you still remember the example from Shivani and Moritz earlier in this morning, I'll be going over it again. If you don't remember, this is a rough flow sheet again of how it looks. And this is what I will implement, or actually it's already implemented, but I will go over the details and try to explain all the possibilities related to this. So basically we have an LD converter. Of course, this is very much simplified. It's only a single reaction for each step, but we have an adiabatic LD converter where hot metal, oxygen, scrap, and lime come in. Then there's the output of gas and a slag. We have tapping and alloying with different alloying materials, and also that produces Gulf gas and slag. The metal bath continues to the next step, which is the degasser, where we add some argon and we reduce the pressure to remove any possible content of oxygen, unwanted nitrogen and nitrogen. And by the end of it, we also perform a de-sulfurizing step for a higher purity of the steel, basically. So, and there we also add carbon carbides. That's basically the idea. Let's go now for the demo. This is the second part. We go, and I'll make this a little bigger. So what I'm using here now is VS Code. VS Code is one of the most common integrated development environments for writing code nowadays. And it is very flexible because it has so much support, and it has all these different kinds of extensions to make coding much, much easier. And one of the very nice features it has is that it supports the Jupyter notebook files. And I already have one open here, which is called secondary steelmaking.ipynb. That is the extension for Jupyter notebooks. And in these files, we can sort of interact with code. It's not like you write a single script once that runs in the background, and then later you have to check out some files and make sense of things in the file explorer. No, here you can interact with the results live. And what is even more interesting is that the memory state is kept. So if you declare a variable, you can later create or add a few more lines of code, and that variable is still available to you to make use of. So if you have a stream result, you can then call it again and then check in more details the contents of that stream, for example. This is basically how you can handle VS Code. And for the notebook, you can also add some notes here. These notebooks are very flexible. You can print many things. You can add even GUI elements. There are so many nice features about it, but I will focus mostly on the coding for ChemApp now. So the first step normally, and it is a requirement, is to let your Python environment know that you want to use the ChemApp package. If you purchase ChemApp for Python, you will be this package is available, and you need to inform which specifically units you want to call or which specific classes you want to call from it. For this example, it's relatively simple. I'm just going to import from the core module the units for the physical properties. And I'm also going to import from the friendly the unit class to change the units in the system, the thermochemical system class to import the database and to also fetch results from the database or information about the database, the phases, and so on. And most importantly for us today, the stream calculation class. As I mentioned before, that is the overarching class that now allows us to do everything here. And there is one helper function that I declare here just for a simple output generation, but don't worry about it. It's not something even so important. There's a lot more things interesting for us. So the first thing is to load the thermochemical database. I will make use of the thermochemical system class. And then the first thing is to simply type .load and inform the name of the CST file that was generated from FactSage. In this case, I have the CST file in the same folder as my Jupyter notebook. So this is quite simple to just, I only need to inform the name of the file. I would say the surname would be the full path name, but that's not necessary now. But then what we can do, just because we load it, is that we can print the results or print the conditions for this database. And there's a simple function for this, get strings of phases and phase constituents. And then you see here the output of what's in there. So we have the gas ideal phase. I'm using the GTOx database. We have the gas ideal, all the phase constituents in here, different gas constituents. And then you see there's a lot of things. So the output is collapsed. So if I just click on scrollable element, there's a lot more phases. So like Moritz explained, also GTOx is made in a way that we don't need to select phases. So I just select all of them. And all of this is very consistent for what we are going to model today. Now I can show you in more details. So the slick phase, the liquid slag or liquid steel, now it's a single liquid solution phase. Phase copy number 1, phase copy number 2, and then, yeah, so many other things. Solid solutions and so on. So you can see quickly here what's in your database if you want to. Then we need to set up the physical units, or even you don't have to, but then in that case, you would just be using the default units. For this case, I have changed the units to make use of ton for amounts, Celsius for temperature, bar for pressure, and joules for energy. And now for the interesting part, how to set up the input composition. So we were talking about this, we are now talking about this is the initial step here. I'm going to create a hot metal input stream. And what I want to point out is that this is the way you would do it in the latest release that is available to customers. But I want to show you the new development, and I will be comparing with what you can do now. So up until now, you would need to create a new stream basically, stream composition in this way. You call the stream calculation class .create st for create stream, of course, and then you provide a name for this stream, an internal name that ChemApp will recognize later, and you set the initial the temperature for it and the pressure, and then you have to use the set IAPC function, which means incoming amount of phase constituent, so that you can define and you need to be aware of what constituents you have or what constituents are available in your database to represent the composition you want. So with this, we make a metal composition here, iron, carbon, silicon, and all the other contents. And basically this would be it. So after this, your stream will be defined really in terms of these phase constituents, which sometimes it's quite okay, depending on the application case. And sometimes it's not if you are interested in slightly different extensive properties for the starting point of your stream. And because of that, now with the development version soon to be available, we have created a new way of generating streams that makes use of the complex formulas that is supported by the core module of ChemApp for Python. With this new way, it becomes even more convenient that in a single command, although it's not a single line because the composition is quite big in this case, but in a single command, you can create a stream. Again, you provide the name of the stream, and then in one of the second argument, it should be an array with the names of all system components or complex formulas you want. So it could be anything here that represents a chemical composition. So if you are talking about, I don't know, calcium carbonate, this would also be allowed, exactly like you would do with Equilib in FactSage. This is not our case now, and this is relatively simple, so I'll continue with system components. And then I also provide the temperature as stated above, as in the other case. But what happens is that internally, after declaring these arguments, the stream calculation class will perform a calculation, equilibrate the phases for this input composition, and the hot metal then starts as an equilibrated stream. And in most cases, this is much more representative of what's really going on in that stream. And then to move on to the other cases for oxygen, scrap, and lime, it's even simpler because the contents of those streams is much smaller. So for oxygen, we have O2, scrap, we have iron, and lime, we have CaO, of course. Always just entering the formula and the amounts and the temperature. In this case, all of these three are at 25 degrees. And then the next part is to perform the reaction here, the LD converter, simplified converter in this case, a single step reaction. And again, up until now, with the latest release, what you would need to do is you use the stream calculation class to set up all the conditions for the reaction for the streams that have been defined already. So you need to be aware of the path you took. Like in this case, we did create this stream. It is available in the memory of the stream calculation class. And then here, everything I set up in the conditions will be used for that particular, for all those streams that were defined up until this point. And then the conditions in this case are the system entropy. For streams, we call, at the moment, they are still called set equilibrium H, although this actually represents set equilibrium delta H. And then entropy is 0. Delta H is 0 for an adiabatic calculation. And we also define the target variable for the equilibrium calculation. So in this case, it would be set equilibrium temperature to, it's actually probably, let me check one thing. Yeah, it should actually be another function because this one is to set the final temperature. There is the one for calculate equilibrium temperature. This is the correct one when you want the temperature to be as the target. So, and the temperature that you provide is only used as a guess. And then that is now okay. And you can then generate from the calculation, once this is called, the calculated EQ, the calculation already happens in the background. And to retrieve results, you can call the get result object function, and then you finally have all the results in a converter in a variable, basically. And also to address the question from Alex from earlier today, this is how you could set up an equilibrium condition for activities of phase constituents, for example. In this case, it's quite flexible if we want it. But then now with the latest version, because this, although it is quite flexible and powerful, we want to make this even simpler for people to arrive, that are first arriving at this universe. And we are now creating a few more functions to simplify all these procedures. So thinking more on the same way that the other tools work, it's easier to make sense of what is going on in a more flow sheeting concept. So In the new way, you can just calculate a adiabatic reaction with this function called reaction adiabatic. And the only thing you need to do is to provide the list of streams that you have created that you want to react at this point. So this is a lot more convenient than what we had before there. And this makes the idea and the notions of the flow sheeting concept much more promptly available, right? We know we can create streams with a single line or a single command, each of them, and then we can also perform one calculation in a single command as well. Because we want to make this even more complex, right? We want to create very interesting modeling approaches and combine many different things in the same flow sheet. So if it becomes a bit tricky to make even the smaller steps, then it's just not so convenient. Now it is convenient. So one thing I just forgot to mention, this function create stream from complex formulas. It's the long name. This is the development version. We will decide exactly on the name for it. And there's also a short name for it just to make the coding a bit nicer and more readable. So going back to the reaction adiabatic case, we have the converter result exactly as a return value from that function. And then the next part is to handle the results of this calculation and then to be able to create the streams to go to the next step. So what we wanted is to split the results into multiple streams. And functionality for this is already available already in the release version also. For every result object, you can call a few different functions. One of them is specifically for the gas phase, create gas stream, and then we will detect which of the phases there in the results are the gas. And this directly gives you the gas stream. But if you want to be more fine-grained, you have more fine-grained control over what you are splitting, you can also just create a stream and specifically say what phases to either exclude or include. So these two arguments could be used at the same time. Here, for example, for the slag, I'm only excluding the gas ideal and slick number one, as Moritz already explained, for the GT oxide base. In this application case, iron and basically the steel bath is in larger amounts for this reaction. So the first copy of the single liquid solution will represent iron. So I'm removing, or will represent the liquid bath. And so I'm removing that part from the slag, and the remaining will be added to the stream. And the other way around, to actually see what's in the steel, we keep only the first liquid solution. A few other things that are available, I think I might even mention them later, but just so you can keep this in mind already. You can also combine streams very easily. Once you have one, there's a function called combine with, and then you just need to inform combine with what, right? And you can do this even once and again, and then you can combine more than one, and then this is all very streamlined. So, and we also have, just to let you know, although it's not needed for this example, the option to split streams by amounts, just as we have in most process modeling tools. And this is how we would do it. So instead of using the results, you would use one of the streams and use the function split at threshold, the threshold for the amount, and then you get one with the lower amount and the other one with the higher amount. Just keep this in mind. And it's all quite flexible as well. And if you want, you can print each stream. We have a template to show all the contents of each streams, the global properties of the stream itself, and also the phases that are available with their contents. I have one, this is the function I created on the top, very simple function just to demonstrate, to show quickly what phases are in each stream. And here we can confirm that for the off the gas, we have the gas ideal. For the steel, we have slick number one. And for slag, everything else, which in this case was, metallic. This is the monoxide solid solution, and C3P for the phosphorus content solid solution as well. Okay, this is a good reminder for me. Before we move on to the next feature that is in the development version, I need to just go over a few of the fundamentals on the density estimation And let's do this now. So, as Moritz also explained on the first day, our colleague Abdul Monin, who unfortunately passed away recently, was working on the density estimation capabilities for ChemApp. And recently I got the chance to conclude his work and to incorporate this in ChemApp for Python. And basically, his work was very interesting. And we are applying the Neumann-Kopp approach, although we have two possible methods for it. We have the density-based estimation based on the pure elements, so Neumann-Kopp from the pure elements, and also the volume-based estimation from the pure methods as well. So all this different data was fitted from data from the materials project and one more source that I don't remember at the moment. And initially, if you just do these estimates, and what we do in the end is actually to take the average of those two, the density-based estimation and the volume-based estimation, because the result is better. But if you just take this for a whole bunch of different chemical groups, all of that are available in the materials project, which are many at 0 Kelvin, you get some correlation, but not exactly what we want. The root mean square error is of 0.77, so it's relatively high. And the nice thing about this work was that it was identified later that once you separate the different materials into their respective chemical groups and wisely selected combination of those groups, you can get a much better fit. So for each single group here, you see the root mean square error going down. In the different cases, we have special combinators for carbonates, sulfates, sulfides, cyanides, things like that. But of course, oxides are a very distinct chemical group, ionic compounds, covalent, and metallic. So this leads to significantly better overall error. And this is what we are adopting. In the results, you can see that at least 60% of compounds show a deviation smaller than 10%. This is the result of the validation, then not with calculation data from materials project, but actually with real data from AHSC and mpds.io, which are paid databases with real data. So this was the validation procedure. And here there's also the comparison between the blue bars here for when you don't group by chemical groups and when you actually do group by chemical groups. And you see that the increase in precision was significant. Okay, so this is the background of how to perform calculations with ChemApp for Python. This is now integrated into ChemApp for Python, so that if your database does not cover density or volumetric data, we will automatically calculate and give you a corresponding volume for such a phase. And this is quite significant given that the error estimates is relatively low, and especially because of the different ratios of the densities for the different materials that we are operating, like in this case for steel metallurgy. This is quite okay, right? The scale would vary much more. And then going back to the demo, how this looks in the end. Remember before, we have to split phases by manually, basically, and make sense of it, of the different phases in the results of a reaction. But now you can just call one function, create streams by density, define the density thresholds, and if you just need to be aware that if you define 2 thresholds, you will have 3 output streams. But this is expected. You should know also a little bit of what to expect. But you don't need to be so much aware of the phases and sometimes even worried about whether you selected the correct phases or not. So, and this is quite enough, right? Just quick comparison. I just wanted to collapse this. Here we had 3 different lines, a few arguments and some things, but now in a single line, you can do the same. And again, the result is exactly the same. monoxide solid solution for the slag case. Here the name is given automatically, so density is below 1, the first threshold, density is below 5, the second threshold, and density is above that, so the rest. Here the metal, the liquid metal. Okay, so now we know how to do things even nicer and more easily. We can progress on the flow sheeting concept. And we move on now to the tapping and alloying case. Again, we need to create these different input streams, but you can see that it's quite simple. 4 lines, 1 line for each input stream, they are created. And then to perform the actual calculation, you can just execute another line, a command. And in this case, it's not adiabatic, but isothermal, taking the temperature as a result from the initial stream that was equilibrated under adiabatic conditions. And again, I need to just inform what will be reacting here. So it's the steel from the first step, from the converted, plus all of the different alloying materials. And then to make things also quite easy, you can just create streams by density again. It's the same thresholds will be correct. So we are done. This is the second step. And for the next part, we have the degasser. I added argon here, although it probably won't make so much difference in this case. This is a very much simplified system, but you can just create in a single line. So I created it. And then again, you perform a reaction. Again, I'm using the isothermal case. Splitting streams, we are done. The degassing case, with the main difference here, just to provide the information, in this case, the degasser, of course, needs a pressure definition, a lower pressure. So in this case, we are using 0.01 bar. That's the only thing. The isothermal reaction also works in this case. And then we have also, for the final part, the de-sulfurizing stage, we need to add the de-sulfurizing agent. In this case, it is calcium carbide. Again, quite simply, we just inform the chemical formula, the amount, and create the stream. Then mix everything up, reaction isothermal, create streams by density, splitting the results. We are through. And here, just a quick comparison. This was a demonstrative example, right? So it's not nice to generate plots and anything, but you can at least see that before the desulfurizing stage, the sulfur content was of 0.1%. And after it went down to, I don't know, 1 per thousand parts in percent. And it works. Basically, it works. One thing that I think the time is a bit tight for me. I cannot go over it, but of course, nowadays, LLMs are available to everyone. And this is a programming tool. LLMs speak programming very well. So I could create, and maybe if there's time, or maybe at the break later, I can also show you, some of you who are interested, how to do this. I can create many things here because I have autopilot in VS Code. If you don't know, not autopilot, Copilot. It's not auto yet. It's only co. But if I hit Control I in my IDE here, I get this prompt window where I can send prompts, and I could select different models here. There are many of them available. I have a paid version, which makes things even easier for me. But then basically this is it, right? You can imagine how this would work. You can ask how to perform certain actions. Given the context that we are in, it will know what to do. And you can also generate, I don't know, schematic outputs from what we did, analysis and all of that. It's very, very interesting. But then I only have 4 minutes left. That's too little. Let me go over to the next part, density estimation. So yeah, a relatively quick note about the effective equilibrium reaction zone. Of course, you can do it here as well, and I can show you, although the example is not running at the moment because I was building while Ömer was presenting, Ömer and Shivana. So I just wanted to show that this is promptly available as well. I have another notebook here. Again, loading databases. I created a function called the bypasser. to simplify things, if you remember from the BOF case, we have the kinetic factors that have a role. And to make that apparent, we need to split the input streams by amounts. So you have then a reactive part and a non-reactive part. And you can do this with a split at threshold. And then if I create a function for this, I'm using Python, I can create functions freely. This makes it much easier in the modeling afterwards. I'll just reduce a little bit. Shouldn't hurt so much. Again, I create the input streams, and then I have a parameterized function to compose my model, and which provides a lot of flexibility for what I want to achieve with this, right? This can be scaled up quite easily. This you can use for parametric studies, of course, and also for optimizations based on your hot metal composition that you can change for each iteration step and things like that. And basically, this is the whole process. You have the bypassers in the beginning with the initial compositions, and then in an iterative loop, you can perform, include the definition of time to a certain extent here. And the different reaction zones are there. Yeah, quite basic, I know. I just don't have much more time also to go over everything. But this would be, and by the way, this is quite short, right? Using all the new functionality, the way to define a very complex system. Of course, it is still a simplified case, but it wouldn't be much more complicated to make this simple case be more complex, because when you create these functions, when you pass streams with these functions, it is quite simple to compose complex flow sheets. And yeah, in my opinion, this is a very short script to make something that is so powerful. So that's the example, quick one for the effective equilibrium reaction zone. And to conclude, you can go even beyond all of this, right? If we want, and we want to harness the full power of Python, you can make use of the concepts that come along with Python. So scaling is, to me, the main advantage of ChemApp for Python, because once things become, I mean, we are talking now for 40 minutes, and basically you already know how to set up a flow sheet. In your day-to-day work, this becomes very simple, and you want to do more. And then scaling is the next step, the obvious next step, right? The composability concept of Python allows you to do this. You can create functions for certain stages, for certain physical phenomena, and later on you can create your own library of functions for your particular needs. And this is very, very powerful, and you can compose very interesting solutions for your applications. Of course, you can use this for optimization of process parameters. Python is known for the data, for support for data crunching, right, and data processing in many different ways. We have the NumPy module, we have SciPy for optimizing anything, basically, on variables. So many things are possible. And I already mentioned briefly the LLM integration, which makes things even more interesting nowadays. And of course, parallel processing, this is, maybe not the biggest highlight here, but it's also something very interesting. Once you finally have your very complex model, you want to be able to run it in parallel to gain in performance. So that's about it. In conclusion, as you have been seeing this table throughout our different presentations over here. Oh, I forgot to put this in the presentation mode, sorry. Yeah. This is the final part, and we can say confidently that the main advantage of ChemApp for Python is how powerful it is for advanced use. Of course, you require some programming knowledge, but everything else can be achieved, and the support is endless for endless applications also. That's it.